velocity fields at different locations and different directions, eventually in all three directions and in 3D, so, or just in one 2D plane and in and at one velocity component. So so it's quite well. Phase contrast MRI gives you quite flexible method to measure flows. It has a lot of problems. So artifacts you see there, for example, you see noise. There are other types of artifacts that are present. Yeah, so we develop basically methods to integrate this data into the models, considering those artifacts, for example. So in short, when you have the anatomy and the flow information, and you have some type of velocity information, you then, by solving inverse problems, so they're trying to merge these two, for example, via some kind of least squares approach, you can augment the information that you have on your phenomenon. So if you have, for example, just an anatomy and a 2D plane, like in this case, with some kind of velocity that goes parallel to the plane, you can indeed parameterize in the model correctly, you can recover the 3D information for velocity and of course for the pressure. Okay, so and that's also the challenge. So depending how much data you have, then it will lead to different type of methods eventually, and so on. So the big picture basically is that when you measure a lot, for example, you measure the 3D velocity field over time, you result in methods that are less complex mathematically, but where the measurement complexity is largely increased. So the scan time and the challenge, so maybe the scan will not work properly and you have to repeat it and so on. So that's the trade-off. And then if you want to go for measurements that are easier to acquire, so you with less complexity, then you will automatically have to increase the mathematical complexity of your problem and also the computational complexity. For example, if you have only few measurements somewhere, then you will have to, say, couple those measurements using some kind of optimization approach. So that, of course, leads to more complications. The thing is that, so image processing people like these approaches, right? Because it's more fancy data that you acquire, but also then you process it easily. So as it is fancy data, then it's also rarely clinically viable. So it's very, very little centers have that. It's increasing, but even the MRI scan vendors, they don't provide it necessarily, commercially. So it's rather, they're rather still research sequences. Of course, there's a big research community, and they meet regularly in order to improve this acquisition and post-processing techniques for this type of data. And well, when you go to less data, for example, these 2D planes with flow information that is just perpendicular to the plane, that's the typical data that you can ask everywhere. So
excuse me, Cristóbal, can we ask questions during your presentation?
Sure, just go ahead. It's better so,
Yeah, I think that Igor has a question. Yes, Igor?
Cristóbal, I just wonder, is it always that if you have more complex input, you have an easier modeling live?
Yes and no. So it depends, If you can handle, so it depends, of course, on the type of data you have. I mean, in the examples I will show in this presentation, yes, right? But for example, if you want to use more data, say you want to, you are able to handle little data, right? So automatically it should be able to handle more data. So you just put more data in as an input, and it should still work fine. But then depend on the optimization, for example, algorithms that you use, that may not be the case, right? So for example, if you want to minimize a function, you use a gradient descent method. The more convex, the more data you have, the more convex gets the function. So the slower is your convergence. But if you use a second order, you use the second order information, then the faster you get. So it's also, of course, you have to have algorithms that are good enough to be able to handle that complexity. But in general, that's the case. So if you have, but it's for sure not for everything, but at least for the examples I will show you, it's the case. So I don't know if that answered kind of your question or is what you wanted to hear.
Yeah, thank you.
Yeah, okay. So, well, I will show you then the first example. So on computing, say, pressure maps from 3D velocity fields, right? So you measure everything, say, up to a certain, of course, spatial resolution, what's given by the image resolution, and then you can directly compute the pressure maps here. So that's, let's say, easy to do. So how you do that? So, well, you have your, say, 4D flow image, so your 3D velocity field over time. You have the Navier-Stokes equation, and then you just plug the velocity in some sense, so we'll see how later, into the equation. So the only unknown that remains in the problem is the pressure gradient. So then you can say directly, you remove the velocity as an unknown because you have measured it, and then you can compute the pressure gradient. Okay, that's, of course, you cannot just compute the pressure gradient, so you have to do some more math to be able to do so. And the thing is, since you are working at a discrete level, there are many ways how to do it, many ways. So I will just focus on the ways that compute pressure maps, not other ways that may compute pressure average over certain locations. So I like pressure maps because then you can just compute the pressure field, for example, here. And then you can probe the pressure field after you compute it. You just can take a look visually, and then you can see how to place your virtual catheter in the lumen. So you don't have to know in advance where are the locations where you are interested in. So then, so this is the basic what the people from image processing have been using for 20 years or so or more. Is a called pressure Poisson equation. So you take the divergence of the gradient of the Navier-Stokes equations, you get the Laplace operator of the pressure equal minus the divergence of the velocity part of the Navier-Stokes equation. So the thing is that, well, one of the problems here that is basically you're then, by solving this, of course, you have to add some boundary conditions, but by solving this, you already are setting your pressure in a very regular space. So you're setting your pressure in H1, and from the Navier-Stokes theory, you know that your pressure is in L2. So you're basically smoothing out eventual physical pressure variations that you may have. And the other thing, of course, that you have here data, which may be corrupted. So you're taking the divergence of that data, and you're taking even higher derivatives of that data. So even second derivatives here. So that also may involve, perturbations of the solution. So then there was some kind of time that there were many methods reported, and we have at the end of a 2018 paper where we have make a summary of this method and make some numerical comparisons. But then I want to just point to this method that actually is called the Stocks Estimator, which is based on some other paper from the 80s, but they basically the people from Prague, from the group you may know, from the Charles University, Jaroslav Hron, Joseph Malek, and PhD students, just took that idea and applied it to estimate pressure. So then basically you take the Navier-Stokes equation in black here as it is, and you just add an additional term which you expect to be small. So if you have if you have perfect data, so U satisfies perfectly the Navier-Stokes equation, then this extra term will be 0, right? So in some sense, you have some kind of consistency, inverse consistency. So you have perfect data, then you get the perfect solution. While that's not necessarily the case here in the case of the other estimator. So you just hope that basically whatever is non-physical in the data is taken by this extra term. So a good thing, though, we believe partially that this works better, is that the pressure now in this context is now back to L2, which is the natural space in the Navier-Stokes equation. So you can try to catch higher, more important pressure gradients than what you actually can do with the other method. So of course you have then a larger problem to solve, but it's still a linear Stokes problem is actually very manageable, even in a laptop for normal spatial resolutions what the image have currently. So so then what we have done, we have basically done two things. So well, we didn't those are not our methods, but what we have done two things. So first, to validate them, okay, we're using experimental data set and patient data set, and also perform mathematical analysis of methods, in particular convergence analysis with respect to discretization. So we have analyzed different discretization strategies, and we have tried to assess, we have performed convergence analysis with respect to the image resolution, and we have tried to assess which method may be more cost effective for a given image resolution. So I will here show you just the experimental results. So here in black, you see this is the, I will show the video here because I think it's nice. So you have here the experiment. So this is the, an aortic phantom with a pump. So it pumps blood through the aorta, and you have a stenosis here. And here the curves show the time variation of the pressure difference between these 2 points. And in black, you see what the catheter gives. And actually, this experiment is repeated over some time. So you get a family of pressure curves, which actually, when you average and you take, you obtain the black curve, and then in gray you see what is the standard deviation of that average. So actually there is quite some variation in the pressure measurements themselves.
Excuse me, Cristóbal, if I can ask another question.
Yeah, sure.
So when you solve this problem for the pressure, do you consider a fixed domain or a variable domain? Because in your example here, clearly the domain changes in time.
In this example, not.
Yeah. What we see at the left is there's like
here
at the end of the period. No, there's this.
No, the domain
at the bottom right. No, what is that? Or just visually represent
the velocity. So it's
the velocity. Okay. Anyway, but in principle, not in this example, but in principle, well, the domain, physically the domain is where changes in time. So when you consider this problem, is it fixed or is it variable?
Yeah. So well, you could do both. Mm-hmm. So it's because from your domain it's just the control volume, right? So mm-hmm. You could just for example here. So here, my mouse. Sorry, I lost the. Yeah. So you can just take a subdomain, right? Fix it and compute the pressure map there. So,
yeah, but
take a moving domain and make it a moving domain problem. So then you should resort into some, for example, some Ale type formulation. So you can do both. What we do here is just we fix the domain.
Okay, but if you take a subdomain, then there is probably a question about boundary conditions, no?
That's a good point. Not for these problems, because for this problem, basically you take some Neumann boundary condition which depends on the data. So you change the domain, you change the boundary condition.
Yeah, okay, yeah, you have the boundary conditions from the data, right?
From the data. And in this case, you always have 0.
Okay, yes, I see. Okay.
Yeah. So this is not a classical PDE problem. It is a PDE, but it's not a forward Navier Stokes PDE where you have to put your boundary conditions in the physical way. Yeah. These are just boundary conditions to be able to solve the problem, which also depend on the data.
Yeah. Okay. I see. Thanks.
Yeah. No, but that's a good question. So then you see here, well, and then you see with different spatial resolutions of the image, you see actually what you get for the flow-based pressure differences. So you see that the ST method, the Stocks Estimator, matches much better the catheter than the PPE, and this difference is also seen in when you increase your pressure gradients. It's more clear, and also then at some point the STE starts failing, and we believe that is not much necessarily about the method. So the method may be not catching higher, more turbulent variations, but also the quality of the data worsens in this case, because you have to change your scan parameters to be able to catch those higher velocities. And then you add some noise and much more noise, for example, to the image. So So I think that there is an issue also at that point with the data. So also the method is also limited, of course, by the quality of the data that you're plugging in. So, but yeah, here it looks that just by changing the way how you solve the problem exactly from the same data makes a big difference in the results. So it pays off to solve this more complicated Stokes problem than the previous one. And see, it is linear. It's a saddle point problem, but it is linear. It's not really a big deal. So yeah, I don't know. Question. So here you have some results with patient data. So these are two subjects. So it's very complicated to get subjects data where you have both for the flow and pressure measurements. You have to do it you have to do a research protocol for that. You don't do it in standard in clinics. So then you see that also in this case, depending on the case, the ST may work better actually, and the results are quite reasonable. I mean, if you think all the assumptions, so I always wonder by these results because all the assumptions and all the modeling and all the physics that are involved just in the catheter-based pressure measurements, so all the electronics and so on, then you have all the physics from the MRI that produce and all the technique that produces the MRI images, and then you have in between the Navier-Stokes equations. So you see results, or you see methods from completely different fields. It's basically coming together into one picture and saying that basically that things work. So I always I'm wondered by these results, how things can work that well. So then, so now I will present you for the flow data and what can you do with that. And also recently, we have developed, we were asking ourselves, since when you get real data, the real data has problems, right? And there are typically, well, basically two types of problems, which are the main problems for the flow and phase contrast in general. Is of course you have in any medical imaging, you have noise. You can see these crazy velocity vectors there on the boundary and so on, or in these parts. And you have also aliasing. So I'm not going to explain where aliasing comes from. I put just here a publication where you can take a deeper look into it. But basically, aliasing and noise are competing. So when you want to reduce noise in the velocity field, then you increase the chances that you will have aliasing. When you have to remove aliasing, then you increase the noise. So that's why it's very common to have, it's very common to have both. You always have noise. So the question is if you will have aliasing or not, and how much noise you have.
Sorry for my ignorance, but what is aliasing?
So aliasing basically is here, okay, physically the velocity you see a part here that doesn't have aliasing. So you have, the flow goes in that direction that I'm pointing with the mouse, okay? But at some point in the highest velocity regions, the velocity actually, the component of the velocity that is the highest swaps. So it becomes negative instead of, or if it's supposed to be negative, then it swaps to be positive. And that is related to how the measurements are obtained with MRI. So the MRI, the velocity is proportional to the angle of a vector, of the magnetization vector of MRI. So if you, basically the angle of that vector is, you take a picture of the angle of that vector, but sometimes you don't know how many laps the vector did during the acquisition. Okay. So then suddenly you get in the angle of the vector you get a difference of 2 pi. You get the true velocity minus 2 pi, and that's why they call aliasing. So graphically.
Yeah, but sorry. Yeah, but sorry. But here, if you subtract 2 pi, for example, or add 2 pi. Well, it will be still perpendicular to the flow, so it does not solve the problem. You see this? Yeah. Or maybe I don't really understand, but you have this vector field with these big red arrows, which is perpendicular to the main flow. Is it due to this aliasing, or it's something different?
No, it's the aliasing. So this is a synthetic data set, so we aliase it explicitly to show this. So then, the highest component of the velocity is the vertical one. So if you take the vector, the highest component is that, and you measure the components separately. So when that component is aliased, it means it swaps. So when that component swaps and the other don't, then you see
Yes.
basically you have some kind of 90-degree rotation, right?
Okay, I see. It's one It's for one component that
It's
you
for
add
one-
to pi, right?
Yeah. You can have
Okay, I see.
aliasing in all components, but aliasing happens usually when the velocity is the highest.
Yeah. Okay.
Yeah,
okay.
which is not, here's the vertical component. Yeah. No, but that's an excellent question.
Okay. Thanks.
So then, well, so there, the data has problems, and well, when you are going to quantify, for example, you have to compute flow rates, you want to take a look, do some more advanced quantification of that data, not just take a look at it, then it's good to know, well, we believe it's good to know where the data is, where you should do this quantification, where you shouldn't. So, so what we do, so how we try to answer the question, we regionally want to know where the data is bad. And how do we're tackling this problem? So, well, we start from the Navier-Stokes equations. Then if we assume that the velocity, the true velocity, is the observed velocity, so the measured velocity, plus some additional error, okay? So we have an additive decomposition of the measurements and the error to obtain the true velocity. Then you plug this into the Navier-Stokes equation, and you get some kind of a new equation for this error, okay? Which looks like the Navier-Stokes equations, but you have a non-zero right-hand side, right? Which is the residual of the Navier-Stokes equation, the velocity part. Similar to what you have in the pressure estimators, the same actually. And you get some additional, a lot of terms. You get some kind of diffusion term, you get the pressure term, you get some convective term, which looks a bit different. You get this additional term, which is not in the Navier-Stokes equation. So you have to close this equation because you need to solve for the pressure. So you can just assume that this is a velocity-free, divergence-free, sorry, error. So that's well, it doesn't necessarily have to be like that, but we see that you obtain more reasonable results when we do like that. So the problem with this, the equation, that is fine to solve somehow. Okay, so you can even apply relative standard methods. Relative, so you have to develop special methods, but you can do that. And the problem is this term already at the continuous level. So this term is not positive definite, actually. And this could lead you to completely unstable results. Luckily, in our simulations, it doesn't, but you have to be aware that that can be the case. So of course you have to complement this with some boundary conditions. What we take exactly as we did for the pressure problem, for this TE problem, and we have developed some basic but tailor-made numerical methods, some stabilized finite elements that take into account this new structure of the problem. So then I'll just give you an example of how this works. This is a real Arctic float. This is volunteer data. And you see here the following. So if this is the velocity, measure velocity, and you see, well, that you have some regions where the flow gets, well, more tricky, right? So here close to the heart and the R, and also here, here also the velocity gets a bit large, and then you have some kind of recirculation here. So actually, it's hard to tell. I wouldn't tell really in advance, couldn't tell in advance which parts are really, say, it's really the flow look like that, or there may be some imaging artifacts. I just don't know. So what if we include this velocity into this new equation that I showed before, into this equation? So we plug the velocity here and we compute this W. And this is how the W looks like. So you see that actually in the descending aorta, even it looks a bit tricky, we get a very small value for this corrective field, which suggested that in general, the flow here, the measurements are pretty correct. So this is actually real. We can really trust our flow measurements. And here we get like quite large values of this W in the aortic arc and in the part close to the heart. So then, for example, if you want to compute, I don't know, flow rate, so you want to compute how much flow is, and you will rather, for example, cut here, right, where the value of the corrector is lower, and not here, right, because you will get worse results. You expect to get worse results. And the nice thing is that this allows you to compare directly with the amplitude of the velocity. So you can compute in the same scale because they are both comparable, right? So then you can really see if you get a W that is comparable in magnitude with the velocity, then it's probably like that's you can really be sure that you can be quite sure that the measurements are not correct. If you get something that's much lower than the observed velocity, then you can well be sure probably that your measurements are correct, are reliable. So that's we actually we have a preprint which is under review about this, also with more results on patients and subjects, and with the finite element method formulation that we developed. Yeah, and we are also planning maybe to use this for image processing, to remove the artifacts actually to guide some image processing methods using this as a guide. So yeah, so that's what we can do more or less when you measure more, right? So you have, say, a full amount of full field measurements, and you can do some stuff. And what I'm going to show you now is what happens if you measure less. And what about yeah? So this leads to PDE constraint inverse problems. So yeah, well, let's go back to the Navier-Stokes equation, but now we will really are going to use, well, eventually more fancy modeling. So we will do, in some cases, we'll do fluid strand interaction. So when you have the Navier-Stokes equations here, you may couple that with a solid, and this is usually done by the boundary conditions, particularly by the, well, from the fluid point of view, by the velocity. I lost my mouse. Okay, and you have, well, typically here it's very important to set up correct or boundary conditions, and in particular in the outlets of the domain we use usually reduced order models, which are basically algebraic differential equations. So so what actually the problem is now, so the idea is to, when you use the integrating data, so doing this PDE constraint optimization, it is necessary because you are in the model has several uncertainties. So I just put some of the uncertainties in the model, the typical uncertainties in the problem. Boundary conditions in the fluid are uncertainties that you will actually estimate from the data, and then therefore you will create the extended data, so the 3D velocity field, for example. But also the elastic properties of the arterial wall are uncertain, but also the geometry, the computational domain is uncertain because you obtain from a medical image, and the medical image has a limited resolution and may have artifacts. So you should, ideally, you should also somehow consider that uncertainty and maybe try to reduce it or estimate it. And I will show you a recent result on that. So how we do that? Well, this is, well, just to set up basic stuff. So we do it using, well, least squares approach, but using sequential estimation. How you relate least squares with sequential estimation? So the simplest way to see it is by taking a look at the linear least squares problem. When you want to estimate a quantity theta, you have a model that relates the parameters theta with the measurements z. And you have some prior knowledge on the parameters theta 0, some variance, some confidence on the parameters, and also some confidence on the data. So when you just minimize this problem, so optimize this problem, you obtain a linear least squares estimator, which basically can be written as the initial estimator 0 plus some corrective term, which is proportional to the difference, to the error between the measurements and your initial estimator. And the proportionality term, which is, well, for the multidimensional case matrix, is the so-called Kalman game and has this form. Okay, so this is, you can solve this problem in just one step by computing that matrix. So this basically contains the Hessian of the least squares function. So this is basic thing, but in the nice thing is that you can extend this to the nonlinear case. This is the famous Kalman filter. So at every time iteration, you give your prior by just taking the result of the previous time step and just propagating with your dynamics, and then you correct that predicted dynamics with the data. And you need to compute at every time step. You need to update the Kalman game. Okay, so then this is of course everything for linear problems, and then you have, I will not give much details in the presentation, but you have efficient extension to nonlinear problems. So nonlinear problems in the sense that, well, the models are nonlinear, but also usually even if you have a linear problem, a linear PDE, for example, then the dependence of the measurements with respect to the parameters is it's nonlinear. So you need to also, if you want to estimate parameters, you need to extend this X, so your dynamic state, using by the parameters. So this leads, of course, when you are estimating using Kalman filter, this gives estimates that vary over time. So if you estimate the parameters, you will see that at every time step you get a new value of the parameters, and you somehow converge over time. So this is to give you an example. So this is a free structure interaction problem emulating some aneurysma, and the idea is to estimate the Young's modulus distribution over the aneurysma by having measurements of the displacements of the wall. So here the measurements were generated by selecting in each region a different Young's modulus. Then you see here the displays of each region, and we add the same noise everywhere in the aneurysm. So you get in the middle a region where you have a very good SNR, signal to noise ratio of the data, because you have a large displacement and a low noise. And the other regions you have a very poor SNR. So when the Kalman filter, you start the filter using from the same value, for example, of the Young's modulus for all regions, then you over time converge with the to the values. When you have good SNR, you converge very well to the right value. When you have poor SNR, your results are worse. So this basically has several examples into one. But the nice thing that you can really tackle very nicely very complex multiphysics problems with this Kalman filter. So you don't need to compute derivatives, adjoints, and anything. So it's quite black box, and you have to just call your software, your forward software, and with some set of parameters and in state, and you get the result, and you process it, and you go over time like that. So just to show something more interesting. So in the this is an experimental validation of this, and you see that this is a tube, a plastic tube, which was measured under an MRI scanner, and we put an elastic trap in one part of the tube to emulate some kind of stiffening, and you see that over time, the Young's modulus of the parts which do not have the strap converge nicely to the value of the Young's modulus that we measure independently in an independent mechanical test outside the scanner. While in the part where you see the strap, you see that the Young's modulus gets a much higher value. And in between, you see that in the region which has only a little bit of the strap has a value in between. So these are some a bit older results, but again, I believe they're still state of the art. And here I will show you some results concerning the handling uncertainties in the geometry. So when you have a medical image, if you have worked with them, you will get something like that, right? So you will get the gray values with, where, for example, if you try to image a vessel, you will have some kind of region that you have to really guess where to put the vessel wall, okay, in your model, in your segmentation. So if this is the thick line is the true vessel, you will have to kind of guess where it is the real boundary of the vessel. And of course, the smaller the vessel, or the larger the voxel with respect to the vessel size, the larger the error you will make when you do this process. So what's the idea? So if if we have an error, so we don't know where is the true geometry, which is here in pink, we only have some segmented geometries, will be the computational geometry. And we will try to compensate for those errors by including additional information. Which type of additional information we can include? Well, if you're doing MRI, you can include velocity measurements. So the question is now how we can actually use velocity measurements, which are not also of limited quality, right? By to compensate for those geometric errors. And the answer is, well, we have to do something with the boundary conditions. So we would somehow use those velocity measurements to estimate boundary conditions. And the idea comes from the following examples. It's a trivial example, so actually it's a good example for exams for students. So if you have a Poisson flow in 2D, for example, in the Poisson flow, you know that, well, if I have the radius r, then you have a 0 velocity here at the boundary, and you have a parabolic profile. Then you can say, okay, I will take a smaller domain of radius small r, and I will include in the boundary of the smaller domain not a 0 velocity boundary condition, but the so-called Navier slip boundary condition. It's a frictional boundary condition. So you say that the tangential stresses are you have a frictional phenomenon. So and the friction coefficient is this coefficient gamma. So when you match these two velocity fields, so you say the velocity field in the left is equal to the velocity field in the right, of course, in the small domain, then this leads to the value of gamma that is written there. So actually you can emulate the same flow using a different types of boundary conditions in a different domain. Okay. So the idea then is the following. So in a more complicated geometry, we don't have that nice analytical relation. But in a more complicated domain, you can extend. Of course, you will need an additional another boundary condition to the frictional one. It's a penetration boundary conditions where you have the penetration coefficient equal to beta, equal to this guy. So now the idea is, okay, I will estimate those coefficients from velocity measurements. Okay. So if you have an inverse solver already that you can somehow estimate boundary conditions, other type of boundary conditions, then you can extend that inverse solver by just including this additional boundary condition and estimate those parameters. So yeah, that's the idea. And so I will show you an example how that works. Of course, we solved this problem using Kalman filtering, but you can also use another approach. So the novelty here is the formulation and the idea of estimating those parameters from velocity data. So I will show you an example. So you have this flow with some stenotic vessel, and then you have we include the wrong geometry. So we have a wrong geometry, and we additionally add some velocity measurements. So this is what happens. So the ground truth. So we compute now the error, which error we make in the pressure drop between the two ends of the vessel. So in black you have the ground truth pressure drop, and in blue you have what happens if you make a mistake in the geometry, but you still apply non-slip boundary conditions there. So you apply the wrong boundary conditions in the geometry. So of course, the larger the error in the geometry, the larger the error in the pressure drop. Okay. So you see also that it's quite sensitive when you have, of course, it's also related to the stenotic and the complexity of the flow, but you see that you have a pretty big sensitivity that while when you make the same error in the geometry, but you compensate that using the this gamma and beta coefficients, then and you estimate those using the velocity, measure velocity, then you get, of course, a very nice improvement in the robustness of the results. So I think these results are very, very good. Yeah, the nice thing that's only 2 parameters more that you have to estimate. So that's quite good results for that simple model. Also, the model of the boundary condition is not exact for this case. So let me.
Sorry, if I can ask a question about that. You have these 2 yellow lines with 2 different velocity compensated 1 millimeter and 2 millimeter difference in the geometry in the area, but the results are the same or very close. So could you comment on that? Because when you have looks like the result should stronger depend on this difference in the domain, isn't it?
Yeah, it depends. You see, they depend, so that you see a difference, but the difference is small because you just estimate another, so for each geometry error, so if you move this dotted line a bit below, okay,
Yeah.
then you will estimate different gamma and betas, right? Remember, in the Poisson flow, gamma depends on the small radius, right?
Yes.
So if you will have a Poisson flow, the result will be always the same. It won't change. Of course, here the boundary condition is not perfect. So for the model, so it doesn't reproduce exactly what you want to reproduce, but it's good enough to obtain a quite robust behavior with respect to the geometrical errors. So
yeah, but sorry, this gamma and beta, which you say compensate, you again find them from the data, right?
Yeah, from the geometry.
Estimated. Okay.
Yeah.
Okay, thanks.
Yeah. Okay. So now I will staying a bit in the geometry thing, but a bit different topic. So I will talk now about the valves. So you have here an well, when you have an aorta, you know that you have between the heart and the aorta, you have valve. So here you don't see the valve, but the valve is there, and you see a bit that is a jet going through the valve, and you see that it's known that when you have a healthy valve or a valve with an obstruction or pathological valve, the flow pattern changes a lot. So there's people investigating the flow patterns, how that affects the aorta. So the question is, that, well, shape matters here, and if we can somehow obtain and maybe it is of clinical interest later to obtain the shape of the valve. And the problem is that if you want to obtain really a 3D shape of an aortic valve, there are just two means to do that. Either you do a CT, and actually a 3 ECG-gated CT, so a cardiac-gated CT, so you involve also more radiation, or you do a transesophageal echography. So you enter with a wire in the esophagus, and you take pictures from the valve there. So this is an invasive procedure. So it's quite challenging to do that. And what about maybe doing completely non-invasively? And so the idea is the following. So if you have for the fall flow, as I showed you before, and you know some fluid mechanics, then you can, well, with your head, picture that the valve should be somewhere there, right? And then this leads to the questions, okay, can we say automatically, mathematically, computationally, identify the shape of the valve from velocity measurements? So what we did is, as a first step, so we keep working on that, is to assume that the valve is an obstruction in the flow, which is represented by the resistive term we call gamma. And this is a function, so it depends on space. It's very large where the valve is present and very low where the valve is absent. So then so the PhD student, so Jorge, the first author here, basically proved that this problem has a minimizer, and you have optimality, well-posed optimality conditions for the Ossin equation. Now we are working on the, he also did it for the Navier-Stokes equation for the stationary case. And
sorry, it is done for a fixed position of the valve, right?
Exactly. So we are assuming that the valve is open and you have a stationary flow.
Right.
Yeah.
Thanks.
When you see the images, and that's a good question. So we believe that that's enough for volume imports, because when you, I don't know if you see me in a video or
yeah, you see you,
okay.
Yes.
So I will do something with my hand. So when you see images of the valve from echocardiogram, for example, you see rather that the valve is closed and then open, and it stays open for a while. And you see that the flow, the jet, is kind of steady. Of course, there are some variations, but the main structure of the flow is steady. So you can, we believe that you can just model that opening position of the valve using a steady flow assumption. So you have to only measure the velocity, catch those measurements at the moment that the valve is open. So So here, you minimize it using the standard optimization algorithm. So we use LBFGS, and this shows you a bit what are the results. So if you have this, if you have perfect measurements, so you have a nice flow, then you can nicely recover at least the shape of the valve here, right? Here we don't use any mass preserving constraints, so that's actually one idea I got this week. We still didn't test it, so to limit really the position where is the valve. So, but here, depending what you see, at least the shape of the valve from the bottom. So then, if you make your image so data worse, it still kind of works. Of course, not that nice, but it still works. And then, of course, if then at noise, then it still kind of work. But yeah, of course, less well. So now we are extending these results to 3D with realistic valve shapes, and we have some experimental data from London that we want to use. And of course, we have those patients for the flow data set that we have from Amsterdam that we also want to use. Yeah. So in which direction are we going actually? So we believe that we want to go further with the quality of data. We want to be able to tackle worse and worse data. And why? Because then you can also speed up measurements. So when you are allowed, when you can't handle that bad data, you can also ask the radiologist for worse quality measurements, so for quicker scans, and then you can still do something with that. So that's actually with the direction that the group is going. And yeah, and that's part of the project we're running now. Well, thank you very much. Yeah,
Okay, thank you very much, Cristóbal, for this very interesting presentation. And I should also note that our audience became larger during your talk. So I think it was a good idea to really go visit. So please, other questions from the audience, please. Well, while people may be thinking about their questions, so in fact, what you presented, there are many different applications. Some of them you mentioned in the beginning. I think, for example, for atherosclerosis, the measurements for this fractional flow reserve, things like that. And for aneurysm also, there are also like the estimate of the danger of this rupture based on this pressure velocity fields and so on. But for example, we work on the modeling of blood clotting in aneurysms. So do you have data like that? Is it possible to get, for example, flow distribution in clotted aneurysm or things like that?
Well, I don't have data like that, but so that's the first answer. You could, yeah, I think you can try to acquire it, right? I mean, so you could, if you have an aneurysm and you want to take, I think that's a nice question that you could try to answer using for the flow.
No, it's exactly the question because well, it's one of many examples where like clotting in aneurysm, not only in aneurysm, but in, for example, another question we work on left atrium appendage, things like that. So flow distribution during clot growth is very important, and it would help us modeling. So the question is whether it is possible to get such data. I mean, not in principle. In principle, well, no, two sub-questions. First, in principle, and then more particularly, for example, do you have or would you have access to such data?
Well, I think it is up. Well, because considering the size of the aneurysm and so on, I think it is. Well, if the patient is stable enough, then you should be able to acquire that data using for the flow. So yeah. I would say yes. The question is now, what is the quality you need? And the data will look like, right? Will look like the things I show you.
Yeah.
I show you here. So I don't know if that's good enough for fitting your modeling. Well, that's another question. But you know, this So you will have something like that, right? So and yeah, that's a separate question, but that you can only answer once you have the data. You have some sample data, and no, well, I don't have that data, but then you should team up with a group who can acquire that data. So.
But you, for example, I suppose that you collaborate with like medical people. How do you get all this data? I mean, probably you have some, well, in hospital you have all these medical people who provide you with the MRI data, right?
Yeah. Yes. So for example, this data is from Chile. Okay.
It's from Chile. Okay.
It's from Chile. Yeah.
So do you have still
the phantom data? This is also from Chile. The 4D flow data for the aortic valves is from Amsterdam. We have some aortic phantoms from London. So it depends what we want to answer.
Yeah.
Where do we get the data? So we don't have a fixed. Yeah. So you need. I think that's the type of data you need to acquire. But if I can check, there was a project in the Netherlands, or there is a running project. Where they have a bunch of 4D flows of aneurysm and abdominal aneurysm. So I don't know if you're interested in abdominal aneurysm.
Yes, yes. I think that. Well, in fact, clotting can occur in any aneurysm. Yes. So yes, it would be interesting. But this is interesting that you say that in fact you get the data from different places, right? And you continue to collaborate.
I basically hunt the data wherever. So I have a question, then I try to ask around who has the data, who can acquire, or I hear that somebody's acquiring some type of data. Then, so I'm also going to the imaging conferences. So that's usually just to hear what they have. And then I go and approach the people and ask. So that's the way to go. Yeah, I don't have but
so isn't it difficult, because my experience of dealing with medical people, that it's very difficult to get data from them.
Yeah, from medical people, yes. From doctors, if you're talking about doctors, but you have to team up with imaging people.
Okay.
So if you team up with imaging groups, then you could get endless amounts of data, because most of the time, but depending on the group, but they have they're basically usually they have a scanner just for themselves for the research. So the largest groups, so they are just scanning all the time. Whatever you need, they just put someone in the scanner, they do it. So right now we have that good collaboration with Berlin where they do that, and they can in one day acquire several volunteers, and so my advice is team up with an imaging group.
Okay.
Yeah.
Good.
And you have to maybe going to imaging conference, for example. This is a 4D flow workshop, which was the last time was before Corona. So I expect that will happen right after Corona again, and it's usually in the UK. So that you can go and maybe or take a look to the people. There is a group. I will search for the flows data for people having acquired for the flow data in aneurysm. I can maybe send you the.
So please, you just don't spend much time on that. But if occasionally you cross like such data, or you work with such data where you have at the same time blood flows and clotting in different geometries, so it would be interesting to see.
I think that data you have to acquire it prospectively. You're not going to cross that data. You need to
search for it.
You need to ask. No. You have to contact a group working on for the flow and setting up a collaboration with them. And because then you need patience, that's also very tricky. So, but I think you have to be very proactive and approaching the right group. There is a group I know they already did a study in abdominal aneurysm. So you may find some patients there with some clotting and others without. I don't know. I can take a look to it.
Okay, good. Thanks. Other questions from the audience, please.
I have a small question, if I may.
Yes, Alexey Belyaev, please. Yes.
Yeah, thank you, Cristóbal, for interesting lecture. My question is, if I understood correctly, your methodology works with the assumption of a Newtonian fluid, and you work with Newtonian rheology. Is it possible to introduce the same method to take into account the non-Newtonian rheology of actual blood, which may be important in stagnation zones, aneurysms, and so on? Or is it not important for this problem?
Which methodology? For example, this one?
Yeah.
Yeah.
This is solving an inverse problem.
Yeah, here if you have a non-Newtonian problem, I assume that, well, if you for the pressure problem, you may be able to include a non-Newtonian because you just insert the data there, right, and you obtain the non-Newtonian behavior because the nonlinearity depends on the velocity. So if you know the velocity, then you just insert it there. Here you may get a nonlinear problem for W. So since it's a time-dependent problem, then you can kind of cleverly tackle that nonlinearity. But here you basically can get a nonlinear problem from W that you have to do something with it. But so of course we assume, more important, that here for these problems that we know the viscosity and the density, right? So we assume a value. And yeah, when in the case of non-Newtonian flows, then you can assume that the coefficients of the non-Newtonian model are known. In the case of the, say, PDE constraint problems, so yeah, here you may have also when I put uncertainties. Oops. No, sorry. When you have uncertainties here, you may also put a red box here in the stress tensor where you may have some parameters related to the non-Newtonian flow. So you could try to estimate those parameters from in the non-Newtonian flow if you have velocity measurements.
Okay, thank you.
But I'm not sure that you will have really enough quality in the data as they are now to do so.
Yeah, I see.
You can give it a try.
Yeah, thanks.
Yeah, thank you. Other questions, please? Igor,
thank you. Thank you, Cristóbal, for a very nice talk. On this slide, just a quick question. Is your elasticity model is linear?
In this specific video, yes. In general, no. I mean, yeah, we can do both.
And I liked your kind of correctors for geometry, where you try to introduce these sleep boundary conditions. But can you use actually to guess the right geometry by trying to find the geometry which effectively minimizes the gamma and beta to make them zero, so to actually achieve the no sleep? What is the right boundary?
Yeah, for sure you can do that. Yeah, that's a try, but that's more complex because you have to do shape optimization. So that's actually when we were thinking about brainstorming about how to do that, then that was of course one approach that we could have tried follow, but that will lead to a more complicated problem. And I think the approach with that's the transpiration and sleep coefficients that's so simple that that it was worth to try, and it worked quite well. So, but of course there are some other I've seen there was previous work and older work where they really estimate the full velocity profile, but for that you need full velocity measurements and assume some regularity on the boundary condition and so on. So that's another way to go. But of course this is very, so the nice thing is this, we don't need almost no data. So we really used just that. So just you take the geometry and just you measure one plane, and measuring one plane in the MRI is one breath also. It's 20 seconds. You get the plane with the velocity on the plane, and that's it. So you can really add it easily to the examination.
Thank you.
Yes, other question, please. Well, I just have a not scientific question, but just curiosity. So, your situation in the Netherlands, how long do you plan to stay there, or is it a permanent position or a temporary position?
I have a tenure track position.
It's a tenure track. Okay.
Yeah. So to be the evaluation is next year. So next year I should go to the evaluation.
It's a teaching position, right? It's a professor position.
Yeah, as a assistant professor now. Yeah.
Assistant professor. Okay.
Yeah.
Okay, very good. Good luck for this evaluation next year. It's a very important step in your career.
Yeah. Thanks.
Okay, if there are no other questions, then thank you very much again for this very interesting presentation. Thanks to all our listeners. And then I think that we will have our next speaker, next talk, Alexey Belyaev, right, in 2 weeks. Anastasia, it's right?
I guess so.
Yeah, yes, it's right.
17th of June, is that right?
Yes, Alexey, you can even announce your talk if you know already. It's the title.
Maybe later I will formulate.
Maybe later. Okay. Yeah. Anyway, so we are kindly invited 2 weeks from now for Alexey talk here in our seminar. Thank you very much for everybody, and bye-bye till the next time.
Bye.
Bye. Thank you.
Bye.
Спасибо.
Bye.
До свидания.